Now let us look at searching in a binary search tree. I have an example of binary search tree here. I will show you the procedure by taking some keys. Suppose I want to search for a key value, that is 25. Then for searching 25, you can see that 25 is present here. Start from root. Take a temporary pointer on the root of a node. Now let us see the procedure. What are the steps? Wherever t is pointing, check for the data and compare with the key. Key is smaller than the data. So if key is small, move t on left child. The next same thing repeating step. Wherever t is pointing, check the data and compare with the key. Key is greater than data in this node. So move t on right side. Then again repeat. Check wherever t is pointing. Data, compare. Yes, it is same. So element is found in that particular node. So that's all. Search is very simple. So in how many comparisons I got this element? 1, 2, 3. 3 comparisons I got the element. Now I'll take one more key element. Key is 40. Start from root. Now start the procedure. Compare data with the key. Key is greater than this data. Move t on right side. Then again repeat. Compare key with the data. Key is equal, matching, element found. So in how many comparisons we found? Just in 2 comparisons I found this. So it means if I am searching for 30, I'll get it in just 1 comparison. So maximum how many comparisons required for searching? If I am searching for these elements which are in the leaf, then the maximum comparisons are dependent on the height of a tree. Yes, the time taken for searching depends on height of a tree. So I can say that the time is order of h, where we know well that height of a binary tree can be minimum log n and maximum n. So height can be from log n to n. So we can go for minimum one and say it is log n. So minimum time is log n. So the time taken for searching in a binary search tree is log n. Next, we look at unsuccessful search. See, these 2 searches, the key elements were present in the tree. So this is successful search. If the key element is not present, then what happens? Let us take a key element, 21. Start searching. Start from root. Compare data with the key. Key is smaller than data. So go on left side. Compare data with the key. Key is greater than this data. So move on right side. Compare key with the data. Key is smaller than this one. So move on the left side. T became null. On the left side of 25 it was null. So T became null. So we have reached the end of binary search tree. So it means the element is not found. Unsuccessful search. So in unsuccessful search also, maximum how many comparisons are done? 1, 2, 3. This is null, so we did not do anything. So maximum comparisons are equal to the height of a tree. So height, we assume that it is minimum, right? We don't assume that it is maximum. We assume it is minimum, so it is log n. Next, I will write down a recursive procedure for performing search in binary search tree. Function name is rsearch, recursive search, which takes pointer to a node, call it as t, and the key element that we want to search. What it will return, I will write at the end. Every time what we have to do, whether that t is null or not null. If it is not null, then we compare. If it is null, means element is not found, and we will stop. So first I will write down if t is null. I will write down failure condition first. If t is null, then return null, means element is not found. Otherwise what? Compare. If key is equal to t's data, if it is matching, then the key is found. Then return t. So it should return a pointer to a node in which that key is found. Else, if key is less than t's data, if it is on the left hand side, then perform search on the left subtree recursively. So it will call itself recursively rsearch by passing t's left child and key, this result will be returned. Otherwise, means it's not matching, it's not less, then definitely it is greater. So search in the right subtree, or search in right subtree. So this is a recursive function for searching in a binary search tree. So this is a recursive function for searching in a binary search tree. And if you observe, first it is comparing for the data and the last statement is calling itself. Either this statement or this statement. So if the last statement in a function is a recursive call, then it is called as a tail recursion, right? So it's a tail recursion. Anyway, we have solved enough recursions. You can understand how this is working. I don't have to trace it and show you. So that's it. This takes log n time, that is equal to the height of a tree for searching. Now let us look at iterative function or iterative function, that is using loop. So search function which takes a pointer to a root node and the key that we want to search. Suppose we want to search for a key 25, then t starts from root. So t is at root. So when we call this function, we'll be passing root to this function. Now what it does? Every time check the data with the key. If key is equal to t's data, if key is equal to t's data, means the data is found. So return t, data is matching. If it is not matching, check if it is less. If it is not matching, check if it is less. If it is less, then go to left side. So else, if key is less than t's data, if so, then move t to left hand side. T will move on left hand side. See, our key is smaller, so it has to move on the left hand side. Otherwise, if the key is greater, then it has to move on the right hand side. In every step, it has to do these things. So else, move t upon right side. So I have already checked the condition for equal and less, otherwise it is greater. So this process I have to repeat. So this should come in a loop, while. Let me trace this once again for the key 25. T is pointing here, that is at root. Then first step, key is equal to data. Is it equal to data? No. Is it less? Key is less? Yes. Move t on left side. Then continue. Again check, is it matching with the data? This 20 and 25, they are not same. Is it less? Key is less, 25 is less than 20? No, greater. So move on the right hand side. Then continue once again. Now check, is it matching? Yes, matching. Return, it will stop. So key is found. Suppose this was not a 25, this was 26. Then, is it matching with the data? No. Key, is it less than this one? Key is not less, it's greater. So move on the right side. So right side is null. T is null. Continue. No need to continue. T became null. So it means this repetition we should do as long as T is not null. If T becomes null, then stop. And when you stop, come out of the loop, then say return null. So this return null, it returns null when the key is not found. If the key is found, it will return here. So that's all with the search process. So this is the so that's all. This is the iterative version of search. So that's all. This is the iterative version of search on a binary search tree. So search time already we have analyzed. So it is log n, height of a tree. So that's all. This is a search procedure for searching in a binary search tree, and it is iterative. Now one thing I would like to show you here, that we saw a recursive function. In a recursive function, it was a tail recursion. Now once we learned that when you convert a recursion into iteration, then you may need stack, right? But here we don't need any stack. This is implemented just using a loop. We don't need any stack. So always it's not required. And when it is a tail recursion, definitely you don't require. If a tail recursion is converted into loop, then you don't need stack. So that's it.